Yeah? Hello? Yeah? Alrighty, so we're going to get rolling here. I don't know about you guys, but I'm excited to be back. Alrighty, so let me let Kenny in. Does anybody Kenley, did you make it in? Anybody see Kenley DeRocher on here?
Yeah, I'm in.
Okay, perfect. Alrighty. Okay, so what we're going to do is we are going to go over heating curves today. Pretty involved mathematically, not complicated. There's just quite a bit of stuff to do. So what we're going to do is we're going to talk about a heating curve. And I've never quite understood why they call these heating curves, because there's nothing curved about them. And pretty much every heating curve looks something like this. Okay, almost everyone looks very similar. Okay, now what we're going to do is we're going to take 50.0 grams of H2O. Now we're going to start out down here at negative 20.0 degrees Celsius. Okay, and we're going to end up here at 130.0 degrees Celsius. Okay, and what we're going to do is we're going to calculate the amount of energy needed to take 50 grams of water from negative 20 degrees Celsius up to 130 degrees Celsius. Okay, across the bottom of this is, or on this, basically the x-axis, this is the heat added. Okay, up the side is my temperature. Now, for water, we should know this value and this value. Okay, does anybody know what this value for water is? Nobody? Well, think about it. If I'm at negative 20 degrees, what is water at this stage? What do I have here? Anybody know?
Isn't it ice?
It's ice, right?
0 and 100.
Okay, so this is 0 degrees Celsius and this is 100 degrees Celsius, right? Because that's where I change from solid to liquid. This is where I change from liquid to gas. Okay? Now, what's going to happen? And this is how, anytime, let's say I go to the freezer, I fill my glass full of ice, right? Okay? That ice is at some kind of negative temperature. Okay, it has to be or it wouldn't be ice, right? So we're going to start at negative 20. We're going to take that ice from negative 20 to 0. To do that, you have to add energy. We're going to calculate that energy, right? Now here, why is this flat? Anybody know why this part of this graph is flat?
It's a phase change.
It's a phase change, right? Which means what, Heslip?
You're not using the energy energy to heat up, you're using it to convert to a different state.
Exactly. That's why my delta T, there's no delta T here. Okay, now on the left side of this, it is all a solid. It's all ice. But on the right side of this, now it has all been converted to a what?
Liquid.
To a liquid. I didn't realize that question was that hard, right? And then it's a liquid, I'm going to heat it up. I'm going to heat it up till it gets to 100. Right when it's 100, it's all still liquid. But as I continue to add heat, over here it's going to turn into a what? Okay, this is going to be really boring if it's just me and Heslop. What's over here? Nobody knows what happens when you continue to heat water? What it does to it?
It turns to a gas.
Oh, it turns to a gas. Was that hard? I didn't realize that question was that hard. Now, to do this, you've got to know roughly two equations. Okay? And they look like this. The first equation is this. Q equals S times M times delta T. That's one of them. And the other one is Q equals M times, and then there's two values you can have here. You can have either H of F or you can have H of V. Okay? H of F is known as the heat of fusion. It's the amount of energy needed to change it from ice or from solid to liquid. H of V is called heat of. Anybody know what the V stands for? Not a soul? Anybody? No? It stands for heat of vaporization.
Volume?
Nope. Vaporization. And that is what converts it from a liquid to a gas. Now, there are 5 values you just need to know. 5 of these. 5 of these. Okay? And I'm just going to give them to you. And if I was you, I would probably write them on my 3x5. Okay? Now, what they are is they're S's, and there's these two. So, what you've got is you're going to have the S for ice. And that is the specific heat for ice. And the specific heat for ice is 0.486 calories per gram degrees Celsius. Okay? And then you've got an S for liquid, H2O. Okay? And that is 1 calorie per gram degrees Celsius. And then you're going to have your S for a gas, H2O, and that's a gaseous H2O, and that is going to be 0.481 calories per gram degrees Celsius. Okay? There are 3 I would just write down on my 3x5. Okay? And you also need to know H of F and H of V. H of F is 79.7 calories per gram. And H of V is 96.2 calories per gram. Okay? Now, those 5 values you just need to have written down because you're going to use them. I will check and see, but I do not remember if they gave them to you on the test. Okay? Now, what we're going to walk through is we're going to walk through the most complicated kind of problem they could give you. I don't think they gave you one this complicated, but this covers everything. And then we'll do a couple where I kind of neck it down a little bit. Now, what we've got to do is we're going to take our ice, which is at -20, and we're going to heat it up to 0. Okay? What is this value going to give me? Anybody know? Not a soul knows what that value is going to be.
Wouldn't that be delta T?
It's my delta T. Exactly, right? So what's my delta T going to be there, Heslop?
Negative 20?
Okay, now delta has no sign. Delta is change.
Just 20.
So it's just 20 degrees, right? So it's 20 degrees Celsius. So I know that this calculation is going to involve this equation, because that's the only equation that involves a delta T, right? So I'm going to go Q equals, now, S. S is specific heat. I'm down here where my water is what? What's my water down here? What state is it in? Now, one of you know what state I'm in down here?
Ice.
I'm ice, right? So why is that important? Was that you, Bella? Why is it important to know that? Why is it important to know that?
Depending on which phase you're in, you're going to have a different S.
Exactly. So for this one, I've got to use my S for ice. So it's going to be 0.486 calories per gram degree Celsius, right? Then I'm going to times that by my mass. And my mass, we said, was 50.0 grams, right? And then I'm going to times that by my delta T. And I believe Hesper told me that my delta T was 20 degrees Celsius, correct? So I do that math, and I take that times that times that, and I'm hoping someone has a calculator, and hopefully more than one, so we get a verification here. I need to know how much energy is required to take ice from negative 20 degrees up to 0. Oh, wait.
$486.
486?
What I got.
Anybody else get 486 calories? We're good there? Alright, so I've got that. I just put a little circle around that because I'm going to use it in a minute. Okay, now I'm ice at 0. So now I'm going to take that ice that's at 0 degrees and I'm going to convert it to liquid at 0 degrees still. This is flat because there's no delta T. If there's no delta T, I now know I'm going to use a different equation. So which one am I going to use? I'm going to use Q equals M times what? Nobody knows which one of these I'm going to use?
Use H to F.
I'm going to use H of F because this is fusion, right? Heat of fusion. So that's going to be my mass again is 50.0 grams. Times that by my H of F, which I told you was 79.7 calories per gram. My grams go away, and what's my answer? Anybody at all? Nobody can do that math?
3,985.
3,985 calories. Anybody back Heslop up?
Yeah.
Yeah? Okay, so we're there. Now all that ice is now water, because now I'm going to liquid, and I'm going to take that liquid water from 0 degrees up to 100 degrees. So now I've got another what? What does that give me? I got another delta T, right? And that delta T tells me which equation I have to use. So I'm going to go here. So I'm going to go Q equals, what else do I have to remember here? Bella, you want to tell them what I have to remember here?
Use the S that's for the liquid.
Exactly, I got to use the S that's for the liquid, right? So I'm going to go 1 calorie per gram degrees Celsius times that by my M, which again is my 50.0 grams, times that by my delta T, and my delta T is what?
$100.
100 degrees Celsius, and I do that math, and I get my Q is what? 5,000. So I got 5,000 calories. I put a circle around it. So now we are all at water, and we're water at 100 degrees. Okay? Now that water is going to boil, right? 100 degrees it boils. And that energy, water doesn't get hotter. It doesn't get hotter until I've converted it all to a gas. So I'm going to use Q equals what? What's this one going to be? M times which one?
Wouldn't it be vaporization one?
Yep, H of V. So that's going to be 50.0 grams times my H of V is 96.2 calories per gram. And that's going to give me what out?
4,810.
4,810 calories. Anybody back her up?
Yeah.
Yeah? Okay. So now, all of my water is now steam. It's now a gas. But it's a gas still at 100 degrees. I've got to take that from 100 degrees up to 130 now, right? I'm going to have to take it. I'm going to do this. I'm going to draw a line down here because we're going to run out of room. And what is my equation going to be now? Bella, what do I have to remember to use right here?
The S for the gas.
S for the gas, so I'm going to go 0.481 calories per gram degrees Celsius, times that by my mass, which is still my 50.0 grams, times that by my delta T, which is now what? What's my delta T now?
Celsius.
30 degrees Celsius. I do that math, and what's my answer?
I got 721.5.
721.5 calories. Anybody back? Cast slip up.
Yep.
Yep. Alrighty. Now we're at my 130.0 degrees. Now, how much total heat did we add to this system? How would I calculate that?
Would you add up the 3 that you used delta T in?
No. Because didn't I add all this energy as well? Didn't I add that energy as well? Yeah, you have to add up them all. So somebody add all them up and give me a value. I'm going to assume someone besides Heslop has a calculator.
I got 15,002.5 or 15002.5.
So 15002.5 calories. Anybody back him up?
Yes.
Okay, now, here's my question. Was that you, Canyon?
Yeah, it was.
You feeling good? How you feeling?
Feeling good.
Good. So, my question is how many sig figs should that answer probably have? Anybody know?
What do you say, 4?
4? Where are you getting 4 from?
Shouldn't it be 3 because of the 50.0?
I would say that. I would say that. I mean, when you look at what's given, it gave me that I started there and that had 3, right? It gave me that I end there, that has 4, and it gave me my mass that has 3. I would say that I go with the least one. I would say probably 3 sig figs, right? My problem's going to be is how am I going to write that in 3 significant figures?
Scientific notation.
Yeah, I would go scientific notation, and I would say 1.50 times 10 to the 2 times 10 to the 4th calories would be what I would do there. That's what I would put as my answer. I will check that on the test before we get any further, or before we go on. Not today, obviously, but before we go on. Okay? Now, that is as complicated as they can give you, because that is taking you from a solid at a temperature to a gas at a temperature. They usually do not do that. Okay? What we did is we gave all five changes here, right? What they usually do is they usually limit themselves to about 3. So what you're going to see, the reason I do that is because this covers everything. This covers everything in this topic, right? But what you're probably going to see is something that looks more like this, okay? And it would say how much energy is needed to convert 37.6 grams of ice at negative 35.4 degrees Celsius to liquid H2O at 62.4 degrees Celsius. Okay? Now, same exact type of question, just a little smaller. Okay? Can anybody tell me why this question is smaller in that sense?
Because you only have to go to liquid, not gas.
Exactly, right? So McGuire, that was you, right? Where is this equation going to stop at? If I look at this, is the big picture.
Would to be at the, like, so the curve up to ice and then the line to liquid, would it stop there?
It's going to stop here on this line.
Yeah, would it stop there, or would it, I don't know.
Well, let's look at it. You're on the right track. If I stop here, I'm still at 0 degrees, right? I've got to be at 62.4, so wouldn't that be up here somewhere?
Yeah.
Yeah, so I'm gonna do this step, I'm gonna do this step, and then I'm gonna stop right there. So I'm really only gonna have to do 1, 2, 3 calculations, where the other one we had to do 5. Okay? So my first one is gonna be to get my ice, right? I'm here. I'm gonna get my ice from negative 35.4 up to what? Where do I got to get that ice? I got to get it up to 0, right? So I'm going to use this one. So I'm going to go Q equals, and I already know these values, so it's really the same exact kind of problem, right? I'm going to go 0.486 calories per gram degrees Celsius. I'm going to times that by what? What's going to go next right here? Sorry, let me slide this back up. So 37.6 grams. Then I'm going to times that by what? What goes next?
35.4.
35.4 degrees Celsius. And I do all that math and I get what?
Do you want it with sig figs or no?
I would just do it, and then when we're done, we'll go sig figs.
Okay. 646.88544.
That's plenty. 0.88 calories. Okay, so we're good to there. Then I'm just going to put a circle around that because I'm going to use that in a minute, right? Okay, then what am I going to do? Right now, by adding that much energy, I have taken my ice from negative 35.4 up to 0. Now what do I have to do with that ice?
Go to a liquid.
I've got to convert it to a liquid, right? So now I'm going to use that other equation, and that is going to be Q equals what? What value do I have to remember to use here?
H of F.
H of F, right? So I'm going to go 79.7 calories per gram, and I'm going to times that by my what?
$37.6.
37.6 grams. My grams go away. My answer is, anybody?
$2,996.72
2,996.72 calories, and I'm going to hold on to it. Okay? And then, what do I have to do? What's this last step going to be? Because right now, I'm all a liquid, but I'm a liquid still at what? What temperature is my liquid at?
0.
It's at 0 degrees, right? Now I've got to take that water at 0 degrees and I've got to raise it up to what?
62.4.
62.4, which is basically going to be my what? What's that 62.4 going to be?
Your delta T.
My delta T, right? What else do I have to remember here for this equation? To make sure and do what?
Your delta T.
Your delta T.
Your delta T.
Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T. Your delta T.
Yep, I got to make sure and use the right S, right? So this is going to be 1.0 calories per gram degrees Celsius. I'm going to times that by what?
$62.4.
Before that. There's one value that'll be in every calculation you do, and that's the mass. I got to have my mass in there, which is 37.6 grams, then my 62.4 degrees Celsius. My grams go away, my degrees Celsius go away, and that's going to leave me with what?
$2,346.24.
Okay, so that's that. So, I've gone from negative 35.4 degrees Celsius ice up to 60.42 degrees Celsius water. And to find my total energy, I'm going to take that value, and that value, and I'm going to add them up. What do I get? It shouldn't take that long to add up those three numbers. Anybody?
Do you want it in sig figs or?
Either way, what do you got?
I got 5,989.84.
5,989.84 calories. So I would probably go back to my original Mendenhall and say, okay, I got 3 sig figs, 3 sig figs, 3 sig figs. What would that be in 3 sig figs?
Um, 5,990.
5,990 calories. Anybody get that besides Mendenhall?
Yes.
Okay.
Yeah.
Alrighty. Alrighty, so we're going to go lazy handy gamey. Okay. And just like last time we were doing this, just when you get it, just call out a number. Next person call out the next number. And we need to hurry because we only have 11 more minutes. Alright, so here we go. So how much energy Alrighty, so okay, so how much energy would be needed to take 27.6 grams of 40 degrees water to steam at 127 degrees Celsius? Okay, so we're starting as water at 40. I've got to take that water and I've got to heat it up to 100. I've got to convert it from water to steam at 100. And I've got to heat that steam up from 100 to 127 degrees. And I need 7 hands. Not 7 hands. We need to get to number 7, and you've got 9 minutes So faster, Daniel's son. Go.
One.
Two.
Three. Four.
Three more. We gonna get three more?
I'll take one. What number are we on?
We should be on 5, right? Didn't I?
I got 5.
Okay, did I had a 4, I think.
6.
One more?
7.
Perfect. Alrighty. Okay, so who was 3?
Me.
Okay, what do we got? What's my first step gonna be?
You would do Q times M times H of B.
So for Y.
What did I put down?
Look, I'm starting at 40, correct?
What?
I'm starting at 40 degrees, correct? before I can convert this, I've first got to get it to where? Then I got to go from
127.
no, but I've got to go from 40 up to what first? Don't I have to go from 40 degrees up to 100 degrees first? Before I can convert.
Oh.
You see what I'm saying? So this first step should be my S of water, which is 1.0 calories per gram degrees Celsius, times my mass, which was 27.6 grams, times my delta T, which is 60.0 degrees Celsius. Anybody get that?
Yep.
What do you got?
Yeah.
What do you got for a value here?
1,656 calories.
1,656 calories. Now, I'm at 100 degrees. Now I'm going to convert it from liquid to a what?
A gas.
Now I'm going to go from liquid to gas, and that's going to be M times H of V, and that's going to be my 27.6 grams times my H of V, which was 96.2 calories per gram, right? My grams go away, and what do I got there?
$2,655.12.
Anybody back that up?
Yep.
Okay. Now it's all gas. Now as a gas, I'm going to go from 100 degrees Celsius up to 127 degrees Celsius, right? So that's going to be what? What do I got to remember to make sure I do here? Bella? What do I got to make sure I do here?
Use the S of gas.
Use the S for gas, right? Which was, I believe, my 0.481 calories per gram degrees Celsius, right? Times that by my mass, which hasn't changed, 27.6 grams. My delta T, though, now is what? 27 degrees Celsius. I do that math, and I get what out? .44 calories. I add those three up, and what do I get?
$4,669.56.
4,669.56. Put that into 3 cigs. I would say 4,670 calories. Something like that. Anybody verify that?
Yes.
Okay. Alrighty. So, just a couple of things. We're going to do lab number 8. I believe is what Amanda told me. Lab number 8 on Friday. 1/8. Okay. We all good? Hello?
Yep.
Okay. Good to see you. I will be excited to go to school in the morning. Okay, see you guys. Have a good one.
Thank you.
Yep.